Welcome to VTU Physics. In this video, we are going to cover the topic called Heisenberg Uncertainty Principle and applications of Heisenberg Uncertainty Principle. As per latest syllabus 21 PHY 12, we can expect Heisenberg Uncertainty Principle is for 2 marks definition and very important derivation which is coming from applications of Heisenberg Uncertainty Principle. With this, let's start the intro. Welcome to VTU Physics. In this video, we will start with Heisenberg uncertainty definition, uncertainty principle definition. Then we will continue with physical significance and the important topic called application of Heisenberg uncertainty principle. So let us see with the definition for Heisenberg uncertainty principle. It is impossible to determine simultaneously and precisely both position and momentum at a time is called Heisenberg uncertainty principle. What is the Heisenberg uncertainty principle trying to say here is you can find out a position separately or you can find out momentum separately, right? But you can't find out position and momentum at a time. So this is what Heisenberg tried to explain us how it is possible. Okay, so let us take one simple example. Let me take one two-dimensional space, that is x-axis and y-axis. x-axis ನೊಳಗಡೆ time ತಗೊಳ್ಳೋಣ and y-axis ನೊಳಗಡೆ distance ತಗೊಳ್ಳೋಣ. Let me take it as distance in y-axis. Let us consider a electron somewhere around here, and velocity of this electron is 0. Velocity of this electron is 0. That means it is possible to find out the position exactly where the momentum p is equals to mass into velocity, where velocity is 0. That means p is equals to what? 0. ಹಾಗಿದ್ಮೇಲೆ we can find out the position of the electron. If we think that microparticle like electron is a stationary particle, in reality there is no such kind of particles are available. Especially in microparticle, they never, its velocity should not be equal to 0. But here we are just considering, if we thought that velocity of an electron is equals to 0, that means momentum will become 0. Similarly, here we able to find out the position. ಆಯ್ತಾ? So ಹಾಗಿದ್ಮೇಲೆ let us take another example. Once again, two-dimensional space. Here x-axis, y-axis, x-axis ನೊಳಗಡೆ time ತಗೊಳ್ಳೋಣ, y-axis ನೊಳಗಡೆ distance ತಗೊಳ್ಳೋಣ. So this is the curve which we can see. Okay, now this is the one point, this is the another point, and this one is the third point. That means at t1 time, position of the particle is here. At t2 time, position of the particle is here. At t3 time, position of the particle is here. That means velocity should not be equal to 0 of that electron or particle. That means we can find out the momentum, but you can't find out the position of a microparticle. Okay, in this case we find out momentum, in this case we can find out the position. ಬಟ್ ದೀಸ್ ಟೂ ಥಿಂಗ್ಸ್ ಶುಡ್ ನಾಟ್ ಬಿ, ಆರ್ ಇವೆರಡೂ ಕೂಡಿ ಇವೆರಡನ್ನು ಒಂದೇ ಟೈಮ್ದೊಳಗಡೆ ಅಥವಾ ಹೆವಿ ಪ್ರಿಸೈಸ್ಲಿ ಜಾಸ್ತಿ ಎಕ್ಸಾಕ್ಟ್ಲಿ ಹೇಳಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ ಅನ್ನೋದನ್ನು ಹೈಸನ್ಬರ್ಗ್ ಅನ್ಸರ್ಟನಿಟಿ ಪ್ರಿನ್ಸಿಪಲ್ನಲ್ಲಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತಾನೆ. ಸೊ ಹಾಗಿದ್ಮೇಲೆ ಟು ಮಿನಿಮೈಸ್ ದಿ ಎರರ್, ಅವ ಎರರ್ನ ಮಿನಿಮೈಸ್ ಮಾಡಲಿಕ್ಕೆ ಒಂದು ಇಕ್ವೇಷನ್ ಕೊಡ್ತಾನೆ. ವಾಟ್ ಈಸ್ ದ್ಯಾಟ್? ಡೆಲ್ಟಾ ಎಕ್ಸ್ ಇಂಟು ಡೆಲ್ಟಾ ಪಿ ಈಸ್ ಗ್ರೇಟರ್ ದ್ಯಾನ್ ಆರ್ ಈಕ್ವಲ್ ಟು h by 4 pi. What is delta x? Delta x is the position. What is the delta? Delta means x2 minus x1 is nothing but delta x. Similarly, what is delta p? Delta p is the momentum. What is delta means? P2 minus P1, that is delta P, is nearly or greater than or equal to h by 4 pi. What is h? H is the Planck's law. Planck's law or Planck's constant divided by 4 into pi. This is the equation which we have to write when we are writing the definition for Heisenberg uncertainty principle. This is the end of the definition. Here we can expect 2 marks question from the Heisenberg uncertainty principle definition. Next, physical significance of the Heisenberg uncertainty principle. Let us see, there are 2 types of physical significance. First one, as per the uncertainty principle, instead of trying to find out the exact position or a momentum of a microparticle like photon, electron, one should think probability of finding the particle at a certain position or probable value of a momentum of a particle. That means ಇಲ್ಲಿ ಫಸ್ಟ್ physical significance ಒಳಗೆ ಏನು ಹೇಳಕ್ಕೆ ಟ್ರೈ ಮಾಡ್ತಾ ಇದ್ದೇನೆಂದರೆ, if you are going to find out the position of any microparticle, okay, only position. If you are going to find out the momentum of any microparticle, that is also okay. But if you are trying to find out position and momentum of a microparticle, it is highly impossible. So to avoid that, let us talk the probability. Means, is it possible, or ಈಗ ಹೇಗೆ ಹೇಳುತ್ತೆ ಅಂದರೆ probability of finding a particle. ಪಾರ್ಟಿಕಲ್ ಅವೈಲಬಿಲಿಟಿದು ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ ಫೈಂಡ್ ಔಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಟ್ರೈ ಮಾಡಿರಿ. ಡೋಂಟ್ ಗೋ ಬಿಹೈಂಡ್ ಎಕ್ಸಾಕ್ಟ್ ವ್ಯಾಲ್ಯೂ. ಟ್ರೈ ಟು ಮಿನಿಮೈಸ್ ದಿ ಎರರ್. ಆಸ್ ಐ ಸೇಡ್ ಹಿಯರ್, ಇನ್ ದಿಸ್ ಕೇಸ್ ಹೈಸನ್ಬರ್ಗ್ ಟ್ರೈಡ್ ಟು ಮಿನಿಮೈಸ್ ದಿ ಎರರ್ ಆಫ್ ಅ momentum and position of the particle. So by this is the first physical significance. Second one, ಏನು ಹೇಳ್ತಾ ಇದೆ, ದಿ ಅನ್ಸರ್ಟನಿಟಿ ಪ್ರಿನ್ಸಿಪಲ್ ಹ್ಯಾಸ್ ನೋ ಪ್ರಾಕ್ಟಿಕಲ್ ಇಂಪಾರ್ಟೆನ್ಸ್ ಫಾರ್ ಮೈಕ್ರೋ ಪಾರ್ಟಿಕಲ್ಸ್ ವೇರ್ ಡಿ ಬ್ರಾಗ್ಲೆ ವೇವ್ ಲೆಂತ್ ಈಸ್ ನೆಗ್ಲಿಜಿಬಲಿ ಸ್ಮಾಲ್. ದ್ಯಾಟ್ ಮೀನ್ಸ್ ಯಾವುದೇ ಕಾರಣಕ್ಕೂ macro level or macro sized particle, if for example if you have your pen in your hand, that is a macro sized particle. ಆಗಿದ್ದ ಮೇಲೆ ಅದಕ್ಕೇನಾದರೂ ಲ್ಯಾಂಬ್ಡಾ ಇದೆಯಾ? ಇದೆ. ಬಟ್ ಹೌ ಮಚ್ ಇಟ್ ಈಸ್ ದ್ಯಾಟ್? ವೆರಿ 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 ಲೆಸ್. ಹೌ ಮಚ್ ಇಟ್ ಈಸ್ ಲೆಸ್? ವೆರಿ ನೆಗ್ಲಿಜಿಬಲಿ ಸ್ಮಾಲ್. ಡ್ಯೂ ಟು ದ್ಯಾಟ್ ರೀಸನ್ ಫಾರ್ ಅ ಮೈಕ್ರೋಪಾರ್ಟಿಕಲ್ಗೂ ಕೂಡ ವೇವ್ ಲೆಂತ್ ಇದೆ. ಸೊ ಹೌ ವಿ ಗಾಟ್ ದಿಸ್ ವೇವ್ ಲೆಂತ್? ಲ್ಯಾಂಬ್ಡಾ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು h by p, ಆರ್ ಲ್ಯಾಂಬ್ಡಾ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು h by m ಇಂಟು ವಿ. ಎಮ್ ಇಂಟು ವಿ ಅನ್ನೋದೇನು ಇಂಡಿಕೇಟ್ ಮಾಡುತ್ತೆ? ಪಾರ್ಟಿಕಲ್ಲು. ಯಾಂಥ ಪಾರ್ಟಿಕಲ್ಲು? ಮ್ಯಾಕ್ರೋಸೈಸ್ಡ್ ಪಾರ್ಟಿಕಲ್ ಬಗ್ಗೆ ಮಾತನಾಡುತ್ತೆ. ಇಲ್ಲೂ ಕೂಡ ಅದು ಮ್ಯಾಕ್ರೋ ಪಾರ್ಟಿಕಲ್ದು ವೇವ್ ಲೆಂತ್ ಇದೆ, ಬಟ್ ಎಷ್ಟಿದೆ? ನೆಗ್ಲಿಜಿಬಲಿ ಸ್ಮಾಲ್ ಆಗಿರುತ್ತೆ ಅಂತ ಸೆಕೆಂಡ್ ಫಿಸಿಕಲ್ ಸಿಗ್ನಿಫಿಕೆನ್ಸ್ ಒಳಗಡೆ ಇದು ಹೈಸನ್ಬರ್ಗ್ ಅನ್ಸರ್ಟನಿಟಿ ಪ್ರಿನ್ಸಿಪಲ್ ಹೇಳುತ್ತೆ. ದಿಸ್ ಈಸ್ ಆಲ್ಸೋ ವಿ ಕ್ಯಾನ್ ಎಕ್ಸ್ಪೆಕ್ಟ್ 2 marks from this concept. Let us see the very important part of the Heisenberg uncertainty principle application. That is, we need to prove that electron never ever exist inside the nucleus, or we need to test whether electron present inside the nucleus or outside the nucleus. Let us consider one radioactive element inside the box. Okay, so this is a radioactive element. Outside the box, let us take two electroplate. One plate is charged with positive, another one plate is charged with negative term. Now, when we take a radioactive element, there are three kind of radiation. One is gamma radiation, another one is beta radiation, another one is alpha radiation. Now, gamma radiation is due to neutron which is present inside the nucleus. Alpha radiation is due to proton due to proton which is inside the nucleus. Beta radiation is due to electron which is outside the nucleus, but we need to test it. Now, as we know that this is attracted towards the positive plate because electron is negatively charged particle, proton is positively charged particle, neutron is neutrally charged particle. Due to that reason, it will not attract towards negative side or positive side, it will go straight. Okay, so once that electron attracted towards the positive charged particle, there will be a voltage, potential voltage will be developed, and when we tested that energy of that, we got around 3 to 4 mega electron volt. In some textbook they have mentioned 4 to 5 mega electron volt. Okay, this is an experimental result. Now we need to prove it. That means that energy which we are talking about is 3 to 4 mega electron volt or 4 to 5 mega electron volt. If we need to say electron present inside the nucleus, that means electron must have this much amount of energy with electron. Let me take some small example. For example, let us consider different orbital. Name it as E1, E2 and E3. Okay, in E1 energy side there may be one electron, E2 side we have two electron, E3 is empty. Now energy of an E1 state is h nu because 1 into h nu. Energy of E2 energy state is 2 into h nu. Similarly, E3 3 into h nu. This is we already know in the Planck's law. Okay, that means if electron want to stay at E1 energy state, then this electron must have this much energy. If these two electrons want to stay in E2 level, sorry for my throat, in E2 state, these two electrons must have this much energy to stay in E2 energy level. Like this, we are trying to prove, or we are trying to find out the energy of an electron to say whether they are sighting or whether they exist inside the nucleus or outside the nucleus. If that electron have same amount of this much energy, that means electron are exist inside the nucleus. If it is not there, then that means it is outside the nucleus. Let us try to prove it by theoretical explanation. First of all, let us consider a theory of relativity equation, that is energy E is equals to mc square. Take it as equation number 1. Now this m is the mass of the electron which is under motion. Now let us consider rest mass of the electron, that is we denote it as m naught. In that case, the above equation can be written it as E is equals to m naught square into c square divided by under root 1 minus v square by c square, if we are going to consider for rest mass energy. So let us take it as equation number 2. Now that means m is the mass of the electron when electron is under motion. Now we are considering m naught is the rest mass, that means electron is at a stationary position. In that case we need to consider this equation. Once we got this equation, then squaring on both side we we get E square is equals to m naught c square c raised to 4 divided by 1 minus v square by c square. If we solve this equation, then we can write it as m naught square c raised to 4 divided by c square minus v square divided by c square. So denominator will go to numerator, then ultimately we can write it as m naught square c raised to 6 divided by c square minus v square. Okay, so that means E square is equals to m naught square c raised to 6 divided by c square minus v square. Take it as equation number 3. So initially what we done, we consider relativity equation, that is equals to mc square, where m means mass of the electron when it is under motion. Now let us consider the mass of the electron when it is under rest or in a stationary position. In that case we denote it as m naught, and the same equation will be written it as in this form, equation number 2. After that we squared both side, then we got equation number 3. Once we got this equation, let us take momentum, where p, let us consider momentum, that is p is equals to m into v. Now here we know that what is the meaning of m. M is the mass of the particle okay, if the mass of the particle when v is not equal to 0. Now let us consider same equation written for the rest mass. In that case we can write it as p is equals to m naught v divided by under root 1 minus v square by c square. Okay, now squaring both side, take it as equation number 4. Squaring both side and then multiply by c square on both side, we get p square c square equals to m naught square v square c square divided by 1 minus v square by c square. So just rearrange the equation, we will get m naught square v square c raised to 4 divided by c square minus v square. Okay, so rewrite the equation, p square c square equal to m naught square v square c raised to 4 divided by c square minus v square. Now keep it inside the box and let us consider equation number 5. Now the equation number 5 and the above equation number 3, the equation number 3 subtract with each other. In that case we can write it as e square, means left hand side will be written it as it is and right hand side will be written it as it is. So e square minus p square into c square is equals to m naught square c raised to 4 into bracket c square minus v square and c square minus v square. Okay, here I have taken the common term, so that means the 1 and 1 will get cancelled out. The remaining equation will written it as like this: e square is equals to p square c square plus m naught square c raised to 4. Okay, now just common term is c square c raised to 4. So rewrite the above equation. We can write it as e square is equals to c square into p square plus m naught square c raised to square. Here m naught means mass of the electron, that means 9.11 into 10 to the power minus 31 kg. Okay, that we can substitute here m naught. Now c is the velocity of light, that means 3 into 10 to the power 8 meter per second, right? The unknown part is p, that means p is the momentum. P is the momentum. So that means we need to find out what is it. Now for that, let us consider Heisenberg Uncertainty Principle, HUP, where it says delta x into delta p is greater than or equal to h by 4 pi. Okay, now as we know that delta x is indicates the position of the particle, delta p indicates momentum of the particle. Initially we are trying to say that electron inside the nucleus, that means the radius of the or the diameter of the electron is something, a nucleus is something about 5 into 10 to the power minus 15. In some textbook they just mention 10 raised to minus 15. We can consider this one or this one. Let us consider this one. That means delta x is equals to 5 into 10 to the power minus 15 meter. Now take one side known part and another side unknown part, that is delta p is greater than or equal to h by 4 pi 5 into 10 to the power minus 15. Okay, if we substitute the values, h is the Planck's constant. Okay, once we got the Planck's constant and once we calculated this one, we will get the, that is delta p is equals to 1.1 into 10 to the power minus 20 nanosecond. This is the momentum. Delta p is greater than or equal to 1.1 into 10 to the power minus 20 Newton second. Now you can't substitute the same thing in this above equation because here we have delta p, and that too how we got it, by considering delta x, that is uncertainty with the momentum. So to remove the uncertainty with the momentum, we can consider delta P. Instead of writing delta P, we can write it as P greater than or equal to 1.1 into 10 to the power minus 20 Newton second. Okay, now once again substitute in this equation. The equation number is to be written it as equation number 6. Equation number 6. Now if we substitute in that equation, then we can write it as E square is equals to 3 into 10 to the power 8 raised to square into bracket 9 into 10 to the power minus 31 whole square plus 9.11 into 10 to the power minus 31 into 3 into 10 to the power 8 whole square. Okay, if we solve this, we can get it E is equals to, as it is, 3 into 10 to the power 8 whole square. If we solve inside the bracket, we can write it as 1.27 into 10 to the power minus 40 plus 7.469 into 10 to the power minus 44. Okay, so here we are going to consider the second term. We are going to consider the second term to make it less. We are going to consider only second term. If going to consider this term, then that means the value of energy will be high. To avoid that, what we will do, we will consider only minus 44. In that case, first term will be neglected and let us consider second term. And once we consider second term, and if we calculate the equation, then the e square will become greater than or equal to 3.3 into 10 to the power minus 23. If we remove square, then how we can remove it? E is equals to under square root 3.3 into 10 to the power minus 23. Okay, so once we remove from the square root, then E is equals to 3.3 into 10 to the power minus 22 joules. The energy we calculated here in terms of joules. Now we need to convert it into the mega electron volt. That means once we converted, means what is the charge of the electron? 1.6 into 10 to the power minus 23 or something. So this is the charge of the electron. If we divided by this, we will get around E is greater than or equals to 20.6 mega electron volt, or we can write it as E is greater than equal to 20.6 into 10 to the power 6 electron volt. This much energy we are getting theoretically, but experimentally how much we are getting? Only 3 to 4 mega electron volt. This proves electron never ever resides inside the nucleus. This is the end of the derivation. I hope you got to know whatever I tried to explain it in this video. If you like this video, please don't forget to like it, share it with your friends, and please don't forget to subscribe and press the bell icon. With this, let's see you in the next class. Thank you.